Hello and welcome to lesson 12. So today we're going to be talking about limits, which at first you're going to see it and you're going to be like, "Wait a minute. That's a rule? We have to pay attention to that? Why is that a thing?" And don't worry, we'll talk about it as we go. So limits are this idea that state what a value should be rather than what it is. So what a value should be and what it is are sometimes different. Not many times, but there are some times where we just have to double check and make sure that what it is and what it should be line up. Typically, this is so that we don't break the rules of algebra. So the main rule of algebra we're trying not to break here is divide by zero. So let's go to the board. So on the board, let's say that we have a function. So let's say we have f of x, and that's equal to 1 over x minus 2. Okay, so we couldn't divide by 0 here. So this would be an example of a function that's going to break the rules of algebra when x equals 2. And the limit as x approaches 2 of this function is also going to be non-existent, because this function, when we go to draw it out, it looks a little something like, oh, come on, mouse, why are you messing with me? Okay, so we're gonna get a little something like this. So it doesn't go to the same place. So there's no way to not divide by 0 at 2. So the limit as x approaches 2 is going to be the same as the value as x approaches 2. So f of 2, we would say, does not exist. So d n e, so it doesn't exist. And the limit as the function approaches 2 also doesn't exist here, because we're not going to the same value on both sides. The left is going down forever, the right is going up forever. So as we try to get to 2, as we try to get to x equals 2, we're having some problems here. So that's an example where we wouldn't have to worry so much about the limits, because the limits and the value are going to be the same thing. But now let's take a peek at a case where that's not the case. So let's say we do another f of x. Let's say for this f of x, we have x multiplied by x minus 1. So on the bottom, we've got x minus 1. So I know what you're thinking. According to the rules of algebra, I can just cancel this, right? And, well, normally you'd be able to. But in this scenario, because we're talking about the function, and because the function has to be written this way, we're not actually allowed to cancel them the way we would normally using algebra. So we have to leave this function the way it is. So if I try to plug in f of 1, I'm going to get 1 times 1 minus 1 divided by 1 minus 1. And oh no, 1 minus 1 is 0, so I actually am not allowed to obtain this value. The function at 1 is going to be does not exist. So if we were to go ahead and graph this, what this would look like. So this is x equals 2. So this is the point where we don't get what we want. So you'd imagine if we canceled this, it would just look like the y equals x function, which it does everywhere except at 2. So at 2, we actually can't ignore the x, or not at 2. It should be at 1. I'm sorry, that was very silly of me. So x equals 1. So at x equals 1, we're not allowed to ignore the fact that we are dividing by negative 1. So even though these cancel pretty much everywhere, they don't cancel at x equals 1, because I'm dividing by x minus 1. And just due to the fact that I'm dividing by x minus 1, I'm not allowed to have a value here. Now, as you might have noticed, this is only a single point, so the left side and the right side of this function, they're both going to the same place. So there should be a specific number that's there. It's just that it's not actually there. So this is where limits are going to help us out here. So we're going to say limit as x approaches 1 of f of x. So this means now we have this function. So it's the same function. So x minus 1 over x minus 1. But this time, because we're doing a limit, we're actually allowed to use algebra to cancel this out. So according to the limit, It should just be the function is the x function. So if it should just be the x function and x should be 1, so we're supposed to plug in x equals 1, I mean this should just be equal to 1. So the limit should be 1, which would be right about here. So even though there's not anything in there, the limit says, hey, what is supposed to be right here? If we looked from the left, so if we followed along from the left and we followed along from the right, what y value should we be approaching? Turns out that y value is 1. So even though here f of 1 doesn't exist, it's a number we're not allowed to grab because we'd have to divide by 0, the limit as x approaches 1 of this function does exist. So in this case, what we just did there was the limit allowed us to use the laws of algebra inside of a function itself, because functions don't always follow that rule. Generally speaking, they will, but anytime you're dividing by something that might give you a 0, you kind of have to go for the limit in order to figure out what that value should actually be, because if you go and check, you're going to be like, oh, there's nothing there? What the heck is going on? What do you mean it doesn't exist? It exists everywhere else. The algebra says it should exist, but the algebra only applies when we're talking about the limits, because technically that x minus 1 is in the original, so we have to respect that it's there. But the limit lets us kind of ignore that. So now what we're going to do is we're going to look at a situation where we don't have to divide by anything, we don't have to do anything crazy. Let's say we have f of x equals, let's say 2x plus 1. So if we tried to do a limit here, let's say we try to do the limit as x approaches 1. Now you'll notice there's no dividing, there's no real algebra to be done here. So all we're really going to do is we're just going to plug this 1 into the x value. We're going to see what happens. So 2 times 1, it's going to be 2, and then 2 plus 1. Well, it's going to be 3. Okay, then the limit is just 3. And this is an important thing about the limit that a lot of people can get a little hung up on. So we're going to talk about it for a second. So when you get a limit, all you're going to do at first is just try to plug in whatever number you're approaching for x. So just try to plug the number in, see what happens. If what happens is that you get, divide by 0, or you get ln of 0, or some other algebra product where it's like, oh, we can't actually do that. That breaks the rules of how algebra works. Then instead, our job is to try to use those same algebra rules to make the function work in the first place. So like we saw in the previous example, if we apply a limit to it, we can use whatever laws of algebra are necessary in order to cancel it and make it into something that is an actual value. Meanwhile, with the original version of it, we're not allowed to do that. So limits allow us to use algebra to figure out what's missing. Again, they tell us what should be rather than what is. Now, you'll find a lot of the time that these two are the same. That's why limits only really need to work in some specific situations. But for the most part, what should be and what is are the same a lot of times, at least when it comes to limits. But you're going to find a lot of problems where they aren't exactly the same. And when they aren't the same, that's when you need to start using the limit form of stuff. And that is mostly done at the start of calculus. So if you're in, Algebra 1 or Algebra 2, and you're like, oh my goodness, these limit things, they seem complex. Don't worry. We're just taking a look at them. We're going to play around with them a little bit. You won't need to fully work with them until you take Cal 1, which could be a little while. All right, so let's go ahead and go back to the presentation. Okay, so now we're going to look at limits on graphs. So we looked at this a little bit, but when it comes to a limit on a graph, so a limit needs to approach the same number from the left side and from the right side. Now, we don't actually have to know what the function is in order to figure out what the limit is supposed to be. So let's go ahead and go back to the board. And I'll show you an example of what that might look like. So let's say I have a brush. Let's say that, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. So we got our tick marks. Let's say we got a function that does this. Okay, so this x value, so this is x equals -1. So real quick, we're going to do the function at -1, and then we are going to do the limit of the function as x approaches -1. And I say approaches because when we're approaching it, we don't actually get that value, because if we had that number, if we plugged in -1, that's going to be one result, whereas if we're just moving towards -1, that might be a different result. So to put this in context, so if we plug in -1, well, there's not anything there, so we would say that it does not exist. There's not a number there. If I look at -1, it's a big open dot, so there's not anything that's actually there. However, the limit does something a little different. So with the limit, we're following this function. So we're following it along from the left-hand side, and as we get to right here, so this would be at about y equals 1/2. So that's pretty interesting. So from the left side, we get y equals 1/2. So we approach from the right side. So we're following it from the right side. We're just following along this function. There it is. It also says 1/2. So even though there's not a filled in dot there, the limit doesn't care what's actually there. It cares about, well, what happens when I move towards there? What happens when I move towards this -1 on the function? Well, we follow the function, we follow it, and it goes to a y value of 1/2. So that means the limit in that case would be 1/2, because both sides of the function are going to the same y value. So when we approach this -1, we're getting 1/2. So let's do another example. And this is the idea. You want both sides to go to the same place. If you do that, then great, you've got the value perfect. So one more example of this. Let's go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So now let's say we get something a little different. So let's say I got something like this, and this is an open dot right here. And then I go down here. Now there's a closed dot. Oh, that's weird. That's interesting. Okay, so we're going to do f of, so this would be x is -2. So let's go f of -2. So x is equal to -2. And then we will do the limit as x approaches -2 of our function. So you might notice that this is going to be very different from our last example. So whereas our last example, both sides went to the same place and we only had an open dot, now we've got a closed dot and they go to two different places. Oh my goodness, there's so many things happening. So let's just start with the function -2. So if we look at -2, that guy's empty right there. So we're going to ignore him because it's empty, so it doesn't count. So we're going to look right there. Okay, so that filled in dot right there at x equals -2, that's going to be -4. So the function value is -4 because the function doesn't care about what the rest of the graph looks like, or if there's, one open dot or 3 open dots or 1,000,000 open dots. We only care about the one closed dot when we're talking about the value of the function. However, when we're talking about the limit, so now we're going to do that same process. So we're going to follow function from the left-hand side. So as we approach from the left-hand side, we're approaching a y value of y equals 0. So that's what the left-hand side says. So that's what we get when we go from the left. Meanwhile, when we go from the right, we're following. Uh-oh, that's weird. If we approach from the right-hand side, we're getting -4. So the limit can't be two numbers at the same time. That doesn't make sense. So what should this number be is actually, well, we can't really say because it goes to two different places. There's two different numbers it could be. And so if there's not one clear option, then there's no option at all. So we just say does not exist. So most of the time, the problem you'll find is that the function doesn't have a value, but the limit does. But in these rare occasions where there is a splitting between the left and the right side of the function, here we say the limit doesn't exist because they don't go to the same value. And we only get a limit when they do go to the same value. So as far as we're concerned, there's no limit here because, there's a big old jump. Meanwhile, if there wasn't, if they had gone to the same place, we would have said, oh, we know exactly what that limit is. It's, it's whatever number it was. But we didn't get that. We were not that lucky. So anyway, so that's how we do limits, both algebraically. Algebraically, we just do the algebra and we try to plug stuff in. And then with the graphs, well, we look at the graph and we see if we're going to the same place or if we're not going to the same place. So that is going to be it for your little bit of introduction to limits. We will evaluate this specific limit in the synchronous hours. And moving forward, I believe we're going to be talking about how continuity works. Yeah. So we're going to use limits to help us understand how continuity works and discontinuity. But for right now, just go ahead and make sure that you try limits a couple times. Make sure you go ahead and watch the Khan Academy videos. They do a good job of having some extra examples of how limits work and how you can approach them beyond just the ones that you saw here. So definitely check those out. Try out the independent practice questions and go through those. And anyway, you have a great day in the meantime, and I will see you in the next video.